We will start with the third lecture in the special theory of relativity lecture series, and today we will discuss the Galilean transformation and the Lorentz transformation. Inside the Galilean transformation, this is a classical transformation which is under the Newtonian mechanics, and in Galilean transformation, let's suppose that we are having two frames. One frame which is a stationary frame, it is S frame and it is having the spatial coordinates x, y, z, and time is the fourth coordinate. Here another frame which is moving with speed v, it will have its coordinates x prime, y prime, z prime, and t prime. But in the Newtonian mechanics or in the Galilean transformation, we are having the assumption that time is a universal thing which is independent of the motion of the observer or source. So it doesn't depend on time, means the time remains the same for a moving observer as well as stationary observer. So time is t equals t prime. Now we consider these frames, and in these frames we know that Galilean transformation discusses the relative motion. It is considering the space is absolute, the time is absolute, while the time is an independent entity compared to the other types of transformations. Let's draw the coordinate system, and this is the coordinate system. It is the S coordinate system x, y, and z here, and it's a stationary frame S, a time t. Now consider another frame. This frame is moving at a speed v, but we are considering that this speed v is the velocity is constant. So it is an inertial frame of reference a is equal to 0. So let me draw this one, and the x-axis coincides on the x-axis, so it will be explained then, while the y and the z-axis are here is y prime and z prime. So this frame is actually moving at speed v, and now this is the distance it has covered, and this covered distance is speed times the speed multiplied with the time. And now we will do some calculations, and those calculations are now let's say an event is occurring at point P, and both of them are measuring the same event. Now what one frame will say, the frame means both the frames were at t equals t prime equal to 0. They started from the origin here, they were at the same location, and then after time t, this has moved this much distance, and we are here. Now an event is occurring, and that event is occurring at point P. So both the frames are measuring this one, and now let's see how they will measure this. For example, they are measuring the distance of the location. So what this frame will measure? The S frame will measure that the location of the event is equal to x, because it is x distance away from this frame. While if this one will be measuring, then this distance is x prime. This is x prime. So here, this distance is additional, and this is equal to Vt prime. And now I can write that from here, x is equal to x prime plus Vt prime. But is in the linear transformation, we are having t equals to t prime. Then I can write this t prime is t as well, because it will not make any difference here in this transformation, and this is Vt. Now from here I can write that x prime is equal to x minus Vt. What about y-axis? Along the y-axis, the event is only a location along the x-axis, while the y-axis and the z-axis are not being affected. So I will write that y prime is equal to y and z prime is equal to z, while t prime is equal to t. And this I call is the set of equations of the Galilean transformation. Because on this side I am having the s prime coordinates, on this side I am having the s prime coordinates. So wherever you are having the motion of the frame, then the coordinates are changing, while the direction in which you are not having the motion, then they remain the same. Now let's take the derivative of this one. So what it will give us? It will give us the velocity. Here it will be velocity, and similarly here as well. Now if I differentiate it with respect to t, then it will be v prime and equal x over t. It will be v minus, it will be v, right? But we should differentiate between this one and this one. Let's say we write this vx prime and we write this one as v, because this is the differentiation and this is v, while this one, let me write it is x. This is the x, the s frame, while this v is the velocity with which the frame itself is moving, and it is constant in time, it is not varying. So what will happen? This is vx prime equal to vx minus v, the frame velocity, while this is vx, this is the velocity which is in the x frame. So what about this one? Vy prime will be equal to Vy. There is no issue with this one. While Vz prime will be equal to Vz. So we see that the velocities are also being affected in this transformation. And now let's take another derivative of this one. So take the time differential again. So it will give you acceleration. What it will be? It will be the acceleration ax prime is equal to ax, while minus, and this is constant in time, so this will become 0. And this will be again the other velocity, ay prime is equal to ay, and az is equal to az. And something strange came out. We saw that x is not equal to x prime. We saw that vx prime is not equal to vx. But the acceleration in both the frames comes out to be the same. So this is somehow a strange thing here. that why the acceleration in both the frames are in the same. It means there is some issue with the time here, that we have selected t equal to t prime, and there is some issue with this one. That's why the acceleration came to be the same. And now write this thing in the linear algebra form. And to write this in the language of algebra, then I can write the Lorentz transformation is x prime and t prime, because these are the two variables which are changing. And this is equal to 1 minus v 0, 1, and here will be x t. Now again, from here we will get the same result. T equal to t prime from here, and x prime equal to x minus vt. So the same result, but this is just in the language of algebra. And what we say here that space is not the same. Now we talk in terms of space and time. Space is not the same because x is not equal to x prime. But we have assumed this thing, t equal to t prime, and this gave us the result that ax prime is equal to ax. So it is like you are having two frames. One frame is moving at a constant speed, and another frame is stationary. So what the Galilean transformation is telling you, that if time is independent of the motion of the observer, then this frame will say the location of the event is this one, while the moving frame will tell you a different location. So in space they will be different. But when it will come to the time for both, we have assumed the same. We haven't derived this thing. But the Galilean transformation assumes this thing. And here is an issue. While, what about the acceleration? If, for example, they are measuring a body which is accelerating, so both the frame measures the same acceleration. Both the frames measure different positions, different locations in space. Both the frames measure different velocities in the space, but both the frames measure the same acceleration. So this is something strange, that why the acceleration comes out to be the same. You got it? Yes. So here note this point, that this thing actually is coming out due to this assumption, that we say that time in the moving and the rest frame will be the same. So I can say that under Galilean transformation, acceleration is an invariant thing. Acceleration is invariant, it is not changing. Or I can say that the acceleration by the rest while the moving observer comes out to be the same. Okay, so if this thing is clear to you, then we will now go to the other transformations, and we will discuss some aspects of the Galilean transformation in comparison to that one as well. Let's say I consider in inertial frame of reference, and you remember the inertial frame of reference was A equal to 0 frame, or the frame in which the law of inertia holds, means a frame which is moving at a constant speed. So all these assumptions I can apply on an inertial frame of reference. So A equal to 0 means V is equal to constant or uniform, and it will be completely a straight line motion, it will not be a curved motion. Because in the curvature, acceleration will arise. And let's say we are having the two frames, which is S and S prime. So S and S prime are here. Let's say this is a frame S and this is another frame which is S prime. We say that S prime is moving with respect to them, with respect to S. But when you don't have any relative points, any point from which you can relate this motion, then there is no way you can tell that S prime is moving. S prime will consider itself stationary and it will say S is moving. While if the observer is in the S plane, it will say S prime is moving, even if both are moving. So the frame in which the observer is considered as stationary frame as long as it is an inertial frame of reference. So now, let's say we assume one thing like one example. An example is this one, that we are having in the same frame, okay, consider the situation. Let's say this is a frame and this frame is itself moving at, let's say, 30 miles per hour or 30 kilometers per hour. And a person is here and he throws a ball, means rolls it on the surface. And that ball also moves at 20 mph, for example. Now what an observer who is here, this observer will say the ball is, I'm stationary because this is a constant speed and the ball is moving at 20 mph. What this observer will say, who is stationary with respect to this one, this observer will say that the ball is moving at 50 mph in the direction of this frame in which the frame is moving. And the opposite of it is that the person here and he throws this one, it rolls in this direction at, let's say, 20 mph, while the frame is moving in this direction at 30 mph. Now what the observer who is here, this observer sees that the ball is moving at 20 mph. Okay? What this observer is seeing, the ball is moving at 10 mph in the direction of the train. So it depends where the observer is. What is the status of the observer? Right? This observer will find different observation, while this observer will find different observation. Now let's say instead of throwing a ball, the same frame, the same 30 mph, and now this observer just let's say shine a torch here. This observer shine light, and he says that the light is going at a speed of light c. What this observer will say? This observer will say, like this frame is also moving at 30 mph. Or if the frame is moving at 30 mph and the observer shines light in this direction, for example, and he will see that it is C in this way as well. What about this observer? This observer will measure principally according to the Galilean transformation. This should have said that the speed is C plus 30 mph. Or here it is C will be minus from the 30 mph. But he also sees that the speed of the light here is 30 mph. Now this is in contrast to the Galilean transformation. So it means, or in between, for example, we consider another example. Now let's say that this one is going at a speed which is closer to the speed of light. Let's say 0.75 c. The frame is going. And he rolls the ball, let's say 8.5 c. So what should be the speed of the ball according to the Galilean transformation? It is to be 1.25 c. Because as it was becoming 50 mph, now according to this one, 0.5 c the frame is going, 0.75 c the frame is going, while 0.5 c the ball is speeding up. So what it will be? The net speed will be 1.25 c, which is not possible.